Let's do an example problem with a boat bobbing up and down in the water with simple harmonic motion.
Nice, good, healthy fruit juice.
Well, now that that's established for us, we can draw the rest of the scenario, which is the dock. And the problem states that when the boat is bobbing up and down here in the water, right, they can step out of the boat onto the dock when the boat is 10 centimeters below, 10 centimeters above the dock. And that plus or minus 10 centimeters is also half of the amplitude, which is 20 centimeters. So here's a good sinusoidal representation of that position, where you have 0.2 minus 0.2. So at half the amplitude, during this range of positions, they can safely step off. And the question is, what time? What is the time interval between those two positions? That's it. So it actually is going to turn out to be a quite easy problem when we use the basic principles that we've just recently learned. So let's let x be a sine omega t, and that's plus or minus half the amplitude. So the solution to this problem, actually the time where the position is between plus or minus a, when we solve for plus or minus 1/2 the amplitude, we will have the times that are desired here. So the a's go away, and we have sine omega t is sine of, well, what's omega? Omega is 2 pi over t, or square root of k over m, but for our purposes now, 2 pi over t is desired. So that's 1/2. Now we can take the inverse sine of both sides. Inverse sine of this, 2 pi t over t, is inverse sine of 1/2. So let's write that. And inverse sine of 1/2 is just pi over 6. So we can easily solve this for the time. Let's go ahead and do that. Pi times t over 2 pi over 6, which is 12 pi, which is t over 12. So the time, and that really is the time for equilibrium to 0.1 meters. So it's a per side basis, really, is what that is. On a per side basis, 1/12 of the period. So the range of time is period over 6. Whatever the period is, 1/6 of that. And if you look at this, that seems approximately right, 1/6 of this entire range of time. So now let's do a problem that's maybe could be thought of as a hybrid between angular simple harmonic motion and just regular linear. So we have a rod of mass m pivoted in the center. The whole thing is length L, and a regular spring with a spring constant K. But notice it's not a torsion constant spinning this around. Nevertheless, we're going to vibrate. We're going to rotate this rod back and forth. So let's see how we'd approach that. Well, it's given that we're assuming, actually we're not assuming, we have a small angle here specified. So the maximum displacement from the equilibrium is cap theta. And this theta here is a function of time, quite frankly. So some assumptions we can make, since it's a small angle, sine of cap theta is just cap theta. Cosine is 1. And then the question is the second derivative of theta with respect to time have this form, minus omega squared theta? Does it have that sort of form? Because remember, this constant in simple harmonic motion is negative omega squared. Omega is square root of k over m, right? So the constant itself is just k over m for regular simple harmonic motion. So let's see if it fits that form. That'll establish it one way or the other. So the restoring torque is from the stretch of the spring, and the moment arm is, for small angle, just L over 2. So torque is minus L over 2 kx. Kx is the force that the spring applies. And then that's minus L over 2k. What's x? Well, x in this rotating system is L over 2, half this length, times theta. All right, so that is minus L squared over 4 k theta. So since that's torque, that's I alpha, which is I d squared theta dt squared. So the second derivative of the position equation is minus L squared k over 4I theta. Well, it's looking to me like this is going to be a constant. Now the moment of inertia is 1/12 mL squared, pivoting in the center. So we can rewrite this as L squared k theta over 4 times 1/12 mL squared. 4 over 12 is 1/3. The 3 comes up. The L's go away. And we have minus 3k theta over m. Well, 3k over m is our omega squared. This is a constant, so it's proportional to theta. So it does fit the form that we desire, this constant being omega squared. So recognizing that the period is 2 pi over omega, generally, right, we can write what the period is. 2 pi over omega. Omega is square root of this constant. And then we're going to flip it around. So 2 pi square root of m over 3k. This is the same form as regular translational SHM would be if the spring was connected to the center of mass and was just vibrating back and forth. Then it would just be 2 pi square root of m over k. But it's square root of 1/3 times that, because it's easier to grab one end when it's pivoted in the center and oscillate it back and forth than oscillating the entire mass. I'm sure that makes good sense to you. Here's a great little AP physics problem involving dynamics and simple harmonic motion. So we have a kind of a composite system here. We have a kind of like a 2-disc system, kind of like a dumbbell, hooked to a spring, and the whole thing is mass m. Radius r. We're going to pull this back, x, and let it go, and it's going to, well, hopefully we're going to see if this is going to oscillate back and forth in simple harmonic motion. Show that it is simple harmonic motion. Calculate the period. So you can recognize, of course, that this thing has got a moment of inertia, which is going to resist the motion, resist acceleration, and the mass itself obviously resists acceleration. Friction is going to be involved to keep it from slipping or sliding, and so we're going to put a few things together here. Let's go ahead and do that. Solve it dynamically, and then we'll go ahead and solve it again with energy. So a free body force diagram on the disk system. And by the way, this is hooked to it, and the spring is hooked to this connector in such a way it's on a bearing, so there's no twisting of the spring that occurs. So we have kx. When we pull this back, the spring pulls this way with a force kx. Radius and friction is going to pull backward on this disk, on the disk system. As it's accelerated to the right, friction says, no, I don't want you to do that, because I've got to roll this thing up in a clockwise sense, so friction has to be pointing to the left. Sum of torques is, in reality, Fr, friction times radius, is the only torque, which is I alpha. So friction is I times A over R for alpha, and divided by R. The R's go away, and we get 1/2 MA. Now, the sum of the forces, looking at the next equation we need, sum of F is MA, so Kx to the right minus friction, which is actually applied here, is MA. Translational equation. So Kx minus friction, which we already discovered is 1/2 MA, put it back here, is MA, so Kx is 3/2 MA, and A is equal to 2K over 3M, X, which I'm claiming right away is SHM. How can we make such a fast claim? Because the acceleration is proportional to the displacement, which means the force is proportional to the displacement as well. That's the condition required for simple harmonic motion. Let's now finish this up. The 2K over 3M is actually omega squared. So omega is square root of 2k over 3m. So we can write down what the period is, because period is 2 pi divided by omega, so flip this around, square root of 3m over 2k. So how does that period expression comport with regular translational SHM period? Usually m over k, this time it's more. It's square root of 3 halves instead of square root of 2 halves, or just the square root of 1. Well, because you've got the additional moment of inertia for rotation. You got to roll this thing up. So it's harder to oscillate this system than just a frictionless mass system. What a beautiful little problem. Hope you enjoyed that. Well, let's solve this problem using energy. And we recognize that V is in the general form for simple harmonic motion, 2 pi over t squared root of a squared minus x squared. We solved that before using energy for a spring mass system. This will be modified just a little bit. 2 pi over t is omega, so it's omega squared root of a squared minus x squared. So we're going to be looking for this form, and mate with the understanding that that form expresses the velocity of the motion of this system. So let's write out the full energy equation. 1/2 mv squared plus 1/2 I omega squared plus 1/2 kx squared is all the energy in the spring 1/2 ka squared. Halves go away. The have-nots stay. Oh, no, that doesn't make sense. Sorry. All right, so mv squared plus 1/2 mr squared. That's the moment of inertia. Omega squared is v squared over r squared. Remember all this? Sure you do. R's go away. Plus kx squared equals ka squared. So we have 1 mv squared and then a half mv squared. That sounds like 3 halves mv squared. Plus k times a squared minus x squared. I'm sorry, equals. Bring this to the other side. So there we see we're coming up with this form here. So let's write that in the proper way. V squared equals 2k over 3m a squared minus x squared. So it does have this form. Notice those square root. This thing has like been squared already. So that means that this is really omega squared. So that's omega squared a squared minus x squared. So that's the connection. Omega squared is 2k over 3m. And so omega is the square root of that, which is 2 pi over t. Now we can solve for t. So we have the same period that we did solving for it dynamically, which we would expect. And note, as already mentioned, the period is greater than the regular spring mass system on a frictionless surface. And the reason is because of rotational inertia. And we have come to the very last problem of the objectives for mechanics and AP physics, called damped oscillations, and the crowd cheers. And this is mainly a conceptual concern. We're not going to have to rigorously solve the equations for damped oscillators. But here's a regular oscillation, where sum of the forces is minus kx, and we end up with this kind of position with respect to time. Now, if it's a damped oscillation, it means something is diminishing the oscillation. So here's an example of what that looks like graphed. You'll notice that the peaks get less and less. It's diminishing. You'll also notice that the period is stretched out slightly. It takes longer to go through an oscillation. This period is this much time. Originally, it was that much time. So there's a reason for that. It's because there's a new resistive force term, minus BV. So this additional resistance as a function of the speed of motion. So it's kind of like through a viscous medium. If you try and oscillate your hand in a tub of water, the faster you move your hand back and forth, the more strongly the medium resists your motion. So that would be kind of like what we're talking about. Now that means minus kx minus bv is ma. Minus kx minus b dx dt is m d squared x dt squared. So that's the differential equation that needs to be solved for x. Not quite as easy as what we've done. And again, we don't have to do that, but here's the results. X equals a e to the minus b over 2m times t cosine of omega prime t plus v. There's the full expression. And you'll notice that this, as time goes on, has a diminution effect. This gets less and less as t approaches infinity. This approaches 0. Omega prime, because it's a new angular frequency here. And that can be seen by the fact that the time it takes to go through an oscillation, as already mentioned, is a little greater because of this resistive force holding back the actual process of oscillating through the motion. So the amplitude, a e to the minus b over 2mt. Omega prime, instead of being square root of k over m, is now square root of k over m minus b squared over 4m squared, turns out. And this factor here is the particular manner in which the angular frequency is diminished, and you see this additional period. So that's the way it happens. You don't have to memorize that. This is when there is relatively little damping. Now, when a system is critically damped or overdamped, the system will not oscillate, and the frequency then ends up becoming 0. And so what that really means is when you have this thing shoot up, it comes down and then just kind of approaches 0 and never goes below the axis. So it doesn't oscillate. This is how an ideal car is designed. So the shocks on your car, when you go down, poof. It doesn't go boom, boom. It doesn't go boing, boing, boing. If you ever followed a car that's going up and down and up and down and up and down after it hits a bump, the shock absorbers are not doing their job. They're damped only a little bit. They have lost their shock absorbing characteristic, and so it bounces down the road, and you don't want that to happen. You want the springs to compress and soften the bump, but then the shocks will just stop it and steady the car out, and everything is good. So that's how they're designed to work. Now this expression, if it's 0, it's critically damped. Now for that to be 0 means that there is no omega prime. The omega prime is 0. There is no angular frequency, which means it's not oscillating, like I just said. It goes up and then just asymptotically approaches 0. And that would happen when b is 2 square root of m over k. So up here in the numerator, you'd have 4mk. The 4's would go away. One of the m's would go away, and there'd be a k left. K over m here minus k over m, 0. If it's larger than this, if b is larger, and b has to do with the medium and the geometry of the shock absorber in this example, then we have an overdamped situation. Now if it's too overdamped, if you think of your car, if your shock absorber is altogether too shocking, well, if it's too viscous, it will be very shocking as it jolts your body very abruptly. So you have a large force over a small amount of time. So that's not good either. This will conclude the full set of objectives for mechanics, or AP Physics. So you can go ahead and cheer.